And I will share my screen. And I do have here a PDF file, and this PDF file, it's simply the same file that we started last class. If you remember, last class we cover a test called hardness, and the next test on the same file called Charpy impact. And look at the name, okay? So the Charpy is the name of the person who kind of invented this test or came up with the test procedure. However, the focus really is testing the behavior of the metals under impact load. And guys, impact load, it means we're hitting our metal by something. That's the meaning of impact. So you can see here the objective of the test is to kind of find or obtain the amount of energy to simply the amount of energy absorbed by our specimen. And you will see this right away. I know that what does it mean energy and what has to do energy with our test, but you will see this very, very shortly. One of our objective is to do the test at different temperatures, okay, at different temperatures. Now here is a zoom into the machine that does the Charpy impact, which the idea here is super simple. So you can see here there is an arm. This white thing is an arm. At the end of the arm, you can see there is some weight attached to the arm, the end of the arm. And the arm is simply fixed here. So the entire arm can rotate around this point right here. And if you look from this point, if you look from here, from this side, you will see this image, okay? So on the left and right here, this little thing which looks like a hammer head, and this kind of edge right here, it goes down and then hits the metal at the very bottom. Okay, so the idea is you have here an arm. At the end of the arm, there is weight attached to the arm. The entire arm rotates and pivot around this point right here. And then if you look from this side, you will see this. So it means there is a kind of a hammerhead attached to the end of the arm. Now, when we release, so there is a kind of a release here. So this is a release. And the function of this release is to release this arm right here. And you guys probably can guess what happens if I release. It works like a pendulum. So this arm here will start to move down and will keep oscillating, And that's something shouldn't be new. Probably you study this in other, physics class. The thing is, when we lift this arm right here, we have added some energy to the system. When I use my hand to elevate or lift the arm this way, I have added specific amount of energy. This energy, when the arm is in static condition, the energy is pure potential energy. You guys remember the potential energy is measured by multiplying the mass. So the distance from the mass multiplied by the distance to the zero position, like this. So let's say this is H. So the amount of potential energy you give to the system is simply the mass multiplied by the H. As you release the arm, what happened is this guy starts to move. Remember, at this position, we have zero velocity. So that this thing has zero velocity. So all the energy is one form called potential energy. If we remove this handle or remove the release, so the system or this mass will start to go down, okay? As it goes down, what happens is there will be an exchange of energy. So the energy will be translated from potential energy into kinematic energy, which means this mass will gain more speed as it travels down. When the arm is at this position, so it's kind of vertical at this position right here, you know what happens? we have zero potential energy, and all the energy will be, all of it will be kinematic energy, which means the maximum speed will be at the very bottom here. And at the very bottom here, we simply place our specimen. So this square here, this square here is shown in the next slide. So in the next slide, this is the very bottom position of the arm. And as I said, if you remove this specimen, this is our this specimen, which is made out of steel. So if we remove this one, what's going to happen? If I remove this one completely out of the way, can anybody guess what happens? Any thoughts? So you have a pendulum, you lift the pendulum up, you give it energy, you leave the pendulum. It's going to keep oscillating. If you agree, give me thumbs up. So how long is going to oscillate? Anybody knows how long is going to oscillate? Theoretically, if there is no any friction or any air. Can anybody tell me how long is going to oscillate? If you attended any of the physics class, you would know this oscillation will go forever. Forever. It always goes from kinematic to potential, the exchange, but it will go forever. However, because of the friction in the internal, like in this pivot, and also the air friction, it will simply slowly depreciate until it dies and then stop in the middle. If you guys agree, give me thumbs up. Okay, so now the question is, what if we put something on the way? Like, what if we place some metal on the way? So what does it mean? It means at the very bottom position, with this huge mass, with the speed, it will give impact. It will hit our specimen, correct? Now, this is what we will see in the tests. So probably I'll have to show you the test several times. So now it's going to be a video, not a lecture. So I'll show you the video several times because I want you to understand few things. So for that, I'm going to go back to our presentation right here. And unfortunately, I cannot load this video, okay? So it will be in the recording, but I cannot like load really this PowerPoint. The problem is the video is huge because I have it with the highest resolution and I cannot load it. It will be probably 200 megabyte. That's not really economical. So, but anyway, you will see how it works right now. So here is the video, okay? So really, I want you to, before we start, I want you to notice the following. Where is the arm? The arm is in the highest position right now, and it is locked, okay? And one thing I wanted to see is this. There is a index. You can see this is an index, and this is the position of the index before we start the test. So let's run the test, okay?
This is recording, I think. It is recording right now.
Okay.
So yeah, go ahead and...
All right. As I said, I will show you the video several times, but now you get the idea. We give a system, give energy by elevating this arm up, and then we release the arm. So the arm will go with the maximum speed because all the energy will hit this sample at the very bottom. And then you can see what happens. Because this sample is on the way, so it's kind of the sample stopped, took all the energy and stopped. So the system has almost nothing, no energy left in the system. If you agree, please give me thumbs up. So the specimen at the bottom, which is very simple, a small bar, absorbed all the energy, and there is very little energy left in the system. How can we measure the energy? So I'll show you right now how can we measure the energy. Maybe I'll need to show you the video one more time. So if I take this one and I think I need to return it, okay, please try to watch what's going to happen to the index. As the arm rotates, it will also rotate the index. And then what happened is, I want you to imagine before, like not this test, to imagine what happens if there is no sample. What happens if there is no sample? This arm will go and pass the lowest point and will also go to the other side. You guys agree on that? If there is no specimen at down, the arm will go down, cross the bottom, and then go to the other side. And then what this does, it will send this index to somewhere here. Okay, I'll show you with the pointer. So if there is no specimen, you will see this guy will rotate with the arm and will go here. Okay, will go here, which means if it goes here, it means on that there is a scale. It means there is no energy was simply absorbed by the sample. However, because we have a sample right here, down here, and this sample will absorb the energy, you will see the index will be somewhere here. So this is how we measure the energy on that scale. Okay. Now let's watch the video one more time.
This is recording, I think. It is recording right now.
Okay. Okay.
So yeah, go ahead and.
Did you guys watch what happened to the index? Okay. Now what we do is, as I said, what we do is we go here and then look at the index. So here we go. Here is the index. And so this number right here, which is 162.7, okay, that's the maximum number. This tells us how much energy was absorbed by our specimen. How much energy was absorbed by our specimen. You can see here almost all the energy was simply taken by the specimen. And where is the specimen? What happened to the specimen? This is what happened to our specimen. Okay, so simply we hit it this way, so it was hit this way, and then this is the shape. You can see it's still intact and absorbed, just bent and took all the energy. Now what we do next is, as I said, our objective in this test is to observe what happened to the metals if we cool them. And that's something very good question, right? So I have some metals in Calgary here, and it's -30 and -40. Do these metals stay the same under the impact load and has no business with the temperature? You will see this in the test. So what happened is we have some coolers at SAIT, which if you come to the school on Wednesday, I'll show you the coolers. It's right here in my slide. So we have a cooler, and the cooler right here, it has, I think, methylene or something. So this cooler can cool the specimen to very cold temperature. You can read the temperature on this side with our thermometer. It is -56. -56. And we need to leave the specimen in this liquid for 24 hours. For example, I leave it today and I have a test tomorrow same time. So it has to be within this coolant for 24 hours. Then as soon as we measure temperature and it's there for 24 hours, then what we do is we extract using some tools like a scissor. We extract the specimen and quickly put it in the device and repeat the test again. Repeat the test again. Now, I don't have another video after the cooling, but you can tell what happens after the cooling. You can see difference by comparing this to this. Okay, probably you can take two observations. One, I want everyone to look at the scale and please understand that this number in yellow is the amount of energy absorbed by the specimen. And you can see here, almost all the energy was simply absorbed by the specimen. One more observation, look at the specimen, okay? Was it completely broken or torn apart or still intact and just bent? That's something you should observe. If you go to here, that's cool. So that's the cooling part, and we cooled the specimen and we rerun the test. This is what happens. Can anybody tell me what happened to the test? Like, so this is specimen after being cooled to -56 and run the test. And this is the amount of energy absorbed by the specimen. What can you tell from this from those two slides? Any help?
Would it be because the metal is more, the molecules are more compact, causing the metal to be more brittle in the colder temperature rather than the warmer temperature where the metal is going to be more malleable because of the molecules not being so compact?
Okay, thank you so much. So as Russell said, I am not, by the way, I'm not a mechanical engineer, and there is a branch of mechanical engineering called metallurgy. I'm not really that, but what we know is our observation, number one, you can tell when we cool the specimen to a very cold temperature, what happens is we need very little energy to break it. So just like Russell said, if I need very little energy to break it, it means the specimen becomes so brittle, so brittle. When the specimen is ductile, it will absorb the energy. When the specimen is brittle, little energy will break it. And even this word, the brittle, you can also look at the specimen, completely shattered, just like glass, when we cool it to minus 56. While if you go to this slide, you can see very ductile, it's still intact. Yes, it was broken, but still intact. So my point is, and that's the whole experiment is about, is simply to see the effect of the temperature on the behavior of the specimen under impact load. So now I think any question before we continue? Any question? It's very, very, really very simple test. I'm sorry, like I went. Sorry, go ahead.
The specimens are obviously all the exact same machine size.
Everything is the same. Everything like this, all the specimens, they are machined. So they are not random specimens, they are machined. So they have the same size, everything is the same. The only difference between, and even the arm goes on the same level, even the mass at the end is the same. Everything is the same except one thing, which is the temperature. The first one was room temperature, like 21 degrees, and the other test was after cooling the specimen for 24 hours and expose it to really cold temperature. You've seen it in the picture, like minus 56. Now, how many of you started lab number 1? Please show your hands if you finished lab number 1. I'm saying there is something called quiz number 1, and the quiz number 1, it covers 2 labs. If you remember, quiz number 1, it covers 2 labs. If you finish lab number 1, show me your hand, please, and keep it up. It's about 15 questions, 15 questions. That's lab number 1. Lab number 2 is way simpler. Lab number 2, which you already finished, it's way simpler. So what I will do right now, I will stop the recording and will give you 10 minutes, maybe 15 minutes, and to finish your lab number 1. So please go to the part which is called Charpy Impact. There are only 5 questions, which is MCQ, so you can finish it very, very quickly. So please go ahead right now and then do lab number 2 on quiz number 1 and then submit it if you can. So now it's 2:26. What do you think if I come back here at 2:40? 2:40? I'm pretty sure it's very short because the test is very simple and those are only 5 MCQ. You can finish them in a matter of maybe 4 minutes or something. So I'll give you kind of a time to finish it and submit it, and then I'll come back to go through the third test. Okay? I'll stop the recording.